All right, so this is Mr. Dealis here, and I'm going to go over an electrostatics, an electric field problem, specifically from the electric field FET activity numbers 3 and 4. So the scenario that we have here is that placed at the origin, we set up the grid so that way we place at the origin, we have a positive charge. If you want, I can put that in a different color. So we have a positive charge here at the origin. And then 2 meters away, we put a negative charge. So we have a negative charge that's all the way out here. And so we have 2 meters of distance through that entire span. This is 2 meters of distance. And then we place a test charge at a location and find the E field at that location. So that is going to be this location up here. Remember that all test charges are going to be positive. In this case, the charge is at 0, 0, and at 2 meter mark at 2, 0 will be both 1 nanocoulomb, and the test charge just so happens to be also 1 nanocoulomb. So they will all be, okay, all charges, all Q's will be 1 nanocoulomb. So with that said, let's keep in mind that this is 2 meters, but let me go ahead and erase that. And we're going to have that test charge at a distance of 1.4, 0.95. That's its location. In fact, let me bring that up here. And so we have 1.4 and 0.95. Notice how I already broke it down into a couple of right triangles here. And that would leave us a distance of 0.6 meters here between those 2 points. All right, so with that in mind, we want to find the distances between the charges. If we go through Pythagorean theorem, we would find that the length here, let me just call this R1, since I will call this charge 1, and this will be charge 2. Then I'll say this is R1 over here, and say that this is equal to a distance of 1.69 meters. I can do the same thing on the other side where I have the right triangle of 0.95 and 0.6 meters. And that would give me a distance of R2 that is equal to 1.12 meters. Now the question is asking me to find the force. It says use Coulomb's law and calculate the magnitude and direction of the net force on a 1 nanocoulomb test charge at that point. Place an E-field sensor and verify the results. So I'm trying to find the force. First I want to find that force in newtons. So I have a distance between Q1 and my test charge Q here, and a distance between Q2 and the test charge, 1.69 and 1.12 meters respectively. So let's concentrate on one at a time. We're going to do some vector addition, where the force between charge 1, I could say the force acting on the test charge acted on by charge 2, or charge 1 rather. But what I'm going to do is I'm going to just say the force acting by charge 1 onto this test charge. I'm just going to simplify my annotation here. So that's going to be equal to K times Q1 times the test charge over, I know that looks like a 9, so I'll try and make it a little bit different. And that's over R1 squared, the distance between those two charges. That in turn is going to give us the value of K, so that's 9.0 times 10 to the 9th. And let me just leave out my units here just to simplify things a little bit. That's going to be then times 1.0 times 10 to the negative 9th coulombs, because that's the same thing as 1 nanocoulomb, and again times yet another 1.0 times 10 to the negative 9th coulombs. That's all over 1.69 meters squared. Sorry, I'm just now throwing some units in there. But I'm going to take all that. In fact, let me take this, move it over, so that way I can leave a little more room. In fact, even shrink it down a little bit. And so that's going to give me a value of 3.15 times 10 to the negative 9th newtons. So that is the force acting along the hypotenuse there between those two charges. Let me look at force 2, between charge 2 and the test charge. So the force acting along the hypotenuse, along my little green line there, along the 1.12 meter line, I'm going to take the same approach, except it's going to be Q2 in the test charge, and it's a different distance. So again, I have my value of K, so that's 9.0 times 10 to the 9th. And just for reference, that is, I believe, newtons times meters squared over coulombs squared for units, if you wish to see it. But just for space, I'll take that away. So again, that's going to be times the same value of charge. So that's 1.0 times 10 to the negative 9th coulombs times 1.0 times 10 to the negative 9th coulombs. Yes, I know it could be squared. And that's all over r squared, which is going to be 1.12 meters squared. And I like the way that looks better, so that way you recognize that the number and the units are squared there. That's going to give us a value of 7.17 times 10 to the negative 9th newtons. Alright, so if I go back up to here and I were to use some trig to find the angles here, I can find a couple of these angles. Let me find this angle theta in here. I'll just call that theta 1. And that will be equal to 34.16 degrees. So I can just use, let's see, we can say that the, if I prefer, I can use tangent. It's supposed to be the way to go. So if I use that the tangent of angle theta is equal to the opposite over the adjacent, that means it's going to be equal to the 0.95 divided by the 1.4. And so to find the angle theta, I would just simply take the inverse tangent of each side. So basically saying that the theta is equal to the inverse tangent of opposite over adjacent, being the 0.95 over the 1.4, and that gives me the 34.16 degrees. Okay, I'm going to take that same general approach here. Let me say I'm going to find this angle here as theta 2, and I will find that to be 32.28 degrees. And so then with that, I'm going to find what the x and y components are of each of the forces between these charges. So for example, between these two charges here, there is an x and a y component force. I'm going to add that with the x and y component force of Q2 in the test charge. So let me go back and do that. Alright, so if I have a force, I'm going to say force 1, that is equal to 3.15 times 10 to the negative 9th newtons. That's going to be my hypotenuse. And my angle is going to be, as we just said, 34.16 degrees, and this is for force 1. And I'm going to find the force 1 in the x component, and let me extend this a little bit, and the force 1 in the y component. So I'm going to say that the y component is going to be equal to sine theta times the hypotenuse, which is the 3.15 times 10 to the negative 9th newtons, and that will give me the y component. And then here I'm just going to use the cosine of angle theta times the force along the hypotenuse, which again is the 3.15 times 10 to the negative 9th. Let's see, those values, in fact, let me go ahead and put those into a XY data table, so X and Y data table. And so that's going to give me, along the X, it's going to be 2.8 1.6 newtons, and in the y it's going to give me 1.77 newtons. I'm going to do the same thing for the other triangle, except because I put my angle in sort of this weird spot here, I'm going to have to use sine for the x component and cosine for the y. So let's see, I can go about it in this direction. So let's say that it's moving along in that way. I can either use, actually, yeah, so I can extend it down like this. Sorry if it's not to scale, but this is my 32.28 degrees. And again, I'm going to use the sine to find the x component. That'll be times the 7.17 times 10 to the negative 9th. And I'm going to use cosine here for the y component. And let's see what that will give me. That will give me 3.83 and negative 6.06 respectively. I'm going to add those ups, and again, this is for force 1 and for force 2, or charge 1 and charge 2 respectively. And so the resultant force is going to be 6.43 and negative 4.29. Those are just adding up the x's and adding up the y's. Now I'm going to make a new triangle to finish things off, where I just start at my 0 point, if you wish. I just start a new triangle, and I'm going to go in a positive direction from here, 6.43, and then from there I'm going to go into a negative direction, because this is negative. I'm going to go into a negative direction, respectively a negative 4.29, and this is my resultant right here. This is my resultant force. And if I were to do the inverse tangent here, I would find that this is a 33.7 degrees, but recognize that this is a negative 33.7 degrees. Otherwise, I could find this angle out here. That would be a positive angle. In either case, it's acceptable. And the value here is equal to 7.73 times 10 to the negative 9th newtons. And that's what we needed to find. Except for one last thing. Remember that the E field, it wants us to check the E field, and it tells us to divide this value by 1.0 times 10 to the negative 9th. The reason for that is that the E field, remember, is equal to the force per charge. So the force being the 7.73 times 10 to the negative 9th, and the charge, well, the charge that is has a force acting on it has a value of 1 nanocoulomb, otherwise known as 1 times 10 to the negative 9th. So that's why we take this force, let me move all this down, we take this force of 7.73 times 10 to the negative 9th newtons and divide it by the charge, which is 1.0 times 10 to the negative 9th coulombs. So we have newtons per coulomb, which is, by the way, the same thing as volts per meter. Don't worry about that too much. That's a chapter 17 thing, and but just know that those two are the same. That's all you really need to know. All right, so that should give us that value. Again, when this just comes down to a value of 7.73, and so that's going to be newtons per coulomb, or volts per meter. And if you were to put that test charge there, you should get about 7.7 to 8, somewhere in that range, and that would test it out. All right, so hopefully this clarified things. It's vector addition. You need to break everything down into their x and y components and treat it as if there is this force right here, or that charge right there, has two forces acting upon it, as if these two things are just pushing on it or pulling it. Remember that the reason why this became negative is because there is an attractive force. Sorry, I'm going up and down. But there is an attractive force between these two, and there is a repelling force between these two. If there was any confusion there, sorry about that. Hopefully it clarified. All right, so with that, email me if you have any questions, and you guys have a good one. Bye.